I heard this recently that apparently there's some kids who are really young and thought that the way you say goodbye in a conversation is like, comment, subscribe. And
Yes. Yeah,
did
yeah,
we talk
yeah.
about this before? So I thought it was so funny.
I've heard that. I maybe read the same tweet that you did,
Mm.
referencing that.
Yeah, which is quite funny in some ways. It's like,
Quite funny and
mhm,
terrifying.
yeah.
Actually, did you see this piece on the auto-generated content on YouTube for kids?
Or no, I've seen the like Russian content farms where they just unwrap presents or have really weird.
Yeah,
Um,
yeah. Maybe I didn't know that they were Russian content farms, but
well,
I guess
they might
any
not be
maybe
Russian.
maybe
Like,
maybe not Russian, but some sort of
mm,
auto-generated like algorithmic revenue stream, where yeah, I guess like unwrapping presents is one, or it's just like
mm,
all possible combinatorial ways of putting together like the heads of different Disney characters or something like that,
okay.
like floating around in like nonsensical combinations.
Oh,
But that
and when you say algorithmic, do you mean done by computers, or do you mean that just they just follow recipes that only known?
I mean, like there are millions
Mm,
of these videos like put together by
mm,
computers and automatically uploaded to YouTube, specifically with the keywords that are optimized to show up in the next column
mm,
on YouTube. And apparently, it's become such a like genre of like the weird deep web that people have started doing
mm.
parody videos, or like sort of creepypasta weird like weird versions designed to like freak people out. But they've started showing up in like the next video
Okay.
views as well for like and on the channel that's supposed to be for like children.
Yeah. No, I've seen this. I've seen that there's apparently on YouTube. It's very like if you have videos that are targeted towards kids, then you're probably in a good business because kids are the type of people who will watch the same video like over and over and over again. In which there are interesting theories about that, partly because it's comforting to see something that you've seen before, but you'll also just generate tons of ad revenue because you'll get loads of views.
Yeah, yeah,
Um,
yeah. It's just pure search
mm,
engine optimization. But like
mm,
instead of kids being entertained by like things spinning
mm.
on a what is it, a kid's mobile in their crib, they're watching it on YouTube
Yeah,
instead.
it's also crazily addictive, I think, for kids.
Yeah, yeah.
So my sister just had a kid, like a baby, a year or so ago, and
Hmm.
hanging around people who are parents, and it is quite interesting just how powerful that phone or tablet is. Like a kid could be crying their eyes out, and you just give them a phone, and suddenly they're quiet for the next 2 hours.
Yeah, well, I mean,
Um,
it's. I think
like,
it's not just kids. It's just we maybe have like slightly better self control, but like I can
um,
barely pull my eyes away from my screen most of the time.
right.
It does seem to hit something pretty primal.
Yeah, but then it's kind of you have this dilemma as a parent because you're like, I don't want my child to be watching YouTube all day, but then it's so convenient.
Sure, sure.
I don't know. Do you think that's different from
Well,
locking
at
kids
least
in?
uh, back when I was a kid, your parents had to at least like put the VHS tape into the machine
Mm.
and press play or
Yeah.
rewind it occasionally,
Right.
things like that. So it was at least a
Yes.
little bit more effort. But I mean, I think my entire generation was raised by Sesame Street, so at least there it was sort of one studio or a handful of studios that were sort of cranking out content for kids.
Right.
But things with at least some amount of sort of social awareness or some sort of incentive to create things that might at least be a little educational.
Right. Exactly.
I think I learned most of my Spanish from from watching that.
Yeah.
Could at
It's
least
pretty
count
cool.
to 10.
Yeah. Or there's like some kind of face behind it, or some kind of editorial responsibility.
Yeah, yeah.
Um,
There's at
which
least a little bit there.
okay.
Though certainly, your average Hanna-Barbera cartoon was probably just various combinations of talking animals running around and having adventures,
Yeah.
like farmed out to some like very cheap animation studio in I don't know, Korea or something like that.
Mm.
So maybe it's just like a more extreme sort of auto-generated version of that. But yeah, it is weird that you don't have the even a semblance of like a human creator behind so much of it now.
Yeah.
And that there is this direct pipe, through these devices to kids from the internet now.
Right. Exactly. And like less parental supervision. It seems like it's
Yeah.
well, maybe not.
Well, yeah.
We'll see.
I think depends on the parent.
So we should get onto generative models or like
Oh, yeah,
because I know
sure,
that you've
we
worked
can.
on where you with like general GANs and
Yeah, we
things
can
like this.
we can talk all about the machine learning side of things.
But maybe it's too soon. Maybe I don't know. I'm quite curious to. I thought it would be good to start at, like a bit younger and your
Sure. Should we?
university days and how you got into math and physics.
Yeah, sure.
Well,
Now that we've started with childhood, we can we can do the entire I don't know, portrait of the scientist sort of history there. Yeah, I don't know. And
Yeah.
I guess when I wasn't staring at a screen all day, I was the kind of kid who would just scribble scribble notebooks full of numbers and stuff like that. I heard Douglas Hofstadter actually would do the same thing as a kid, but it was just like a weird sort of
his book. His book. I think everyone has.
yeah
GED
exactly.
At this point.
But yeah, how did I get started down that path? No, I would mostly just as soon as I could learn to count to 100, I would just do it over and over and over again until my parents probably just wanted to strangle me.
Oh, cool.
It's like the way that kids now would sing just Let It Go over and over and over again.
Oh, interesting.
You get sort of into that one little obsessive thing is when you're young.
Yeah, I always liked the doubling game. I think that was my favorite game as a kid.
Yeah. I would do that a lot too, and now in computer science, now remembering the powers of 2, I guess, is helpful for figuring out something or other.
Yeah, exactly. It was just kind of fun to see how high you could go before your brain just couldn't keep that big number in your head at the same time.
Yeah,
and I guess this was you wouldn't just Google it, or you wouldn't use a calculator.
You couldn't do it back then. You could use a calculator, but that was obviously cheating.
Yeah, but there was at least one occasion when you had to prove it for yourself and actually sit down and be like, "What's
sure,
8,192 plus
or
8."
Yeah, or when you first learn how to do actually how to do multiplication, you're like, oh, I've got a new tool now. Let me just do this as much as I can.
That's interesting.
And it's as soon as I would have access to calculators to play around with, it would just be I just sort of put certain numbers in and just iterate them over and over again.
Yeah, I remember the first time I learned what the equal sign meant in algebra. That was a big breakthrough moment for me, I think. Where prior to that, there'd always been these rules where it was if you add 6 to one side, then make sure you add 6 to another side. It's why would or change side, change sign, and this kind of thing. And there were these rules that we had, and it wasn't very clear. And then suddenly it was wait, equals means that the 2 things on both sides are exactly the same.
Yeah, right.
And suddenly all these other rules made a lot more sense. And you have inequalities and things, and you divide by -1 or something. It made a lot more sense.
Because when you first learn this stuff, it's just sort of here are symbolic manipulations you can do. It's not always this conceptual thing.
Yeah.
But it's sort of if you just do it enough by muscle memory, suddenly one day you wake up and you're like, oh, okay, I get what this is. But yeah, I guess around the same time that I was doing algebra, I was I don't know how it was where did you grow up again?
In England. Yeah, not too far from here, actually.
I don't know how the math education works here, but for some reason in the United States, every single middle school math class, you have to use a TI-83 graphing calculator, and somehow these things haven't changed since probably the mid-'80s or whenever they came out, and haven't still cost $75 because whatever, because every middle school in America requires you to buy them, so there's no pressure to actually drive down the prices, even though the smartphone that every kid has is more powerful than it now. But yeah, this was one of my first exposures to programming. Even was friends in that class who when we weren't just actually calculating stuff, would be like, whoa, you can make fractals if you put in little programs and stuff. They never really actually teach you the programming side of it. It's just there's always that sort of one kid in the class who sort of finds out this stuff, or maybe their dad is an engineer or something like that. I mean, usually their dad, but and somehow this knowledge just sort of diffuses among the really nerdy 12-year-olds when they're not solving Rubik's cubes or something like this.
Yeah, that's pretty cool, actually. No, I don't think we got graphing calculators until a little bit later than middle school. More high school, I think. That's pretty cool. We had the standard Casio scientific calculators where you had to learn all these. You could at least store numbers, and you could do sine functions and cosines and things like this.
All the basics.
But that's pretty cool. So did you get into programming quite young then, or were you more of a mathematician?
I mean, I guess I was sort of I was exposed to it pretty young. I mean, we always had a computer in the house growing up. But the funny thing is, I think the generation today that grows up with these, sort of slick graphical user interfaces, they're in some ways less likely to become programmers at a young age because all of the interactions with the machine at the very low level have kind of been smoothed away to make it like easier to work with.
Right.
And that's all kind of been pushed onto programmers to make this very sleek product. And our first computer growing up was a Macintosh LC3. And, even that was a fairly polished product compared to the first generation of PCs. And that was not actually where my first programming experience was. That actually came like at summer camp when I stumbled across the like old Commodore 64 that was like tucked away in the corner of the computer lab they had. And, a lot of the counselors were concerned I wasn't getting out and, playing soccer enough or like going canoeing, that I would just sit inside and play Oregon Trail all day.
Oh, sweet. Yeah.
But came across that, and it was, this was like 1995 or 6 or something like this. And, but this was a machine that still had, saved all of its program state out to a tape cassette. So it was like pre-floppy disk even.
Okay. Huh.
But basically all it had was a BASIC interpreter. So like I just had to learn BASIC to do anything with it. And just once you get the idea that, you don't just do something that somebody else has sort of set up for you, but that you can create new things. Obviously the first thing I did was start writing games.
Yeah.
Don't remember exactly what they were, but it was, simple stuff. Or you just write, 10 print hello, 20 go to 10, and see everything blow up. That's pretty much everybody's first program.
Yeah. That's pretty cool.
But yeah. So that was it. Was just this sort of having this old computer where the only thing you could do was program, and having a manual sitting next to it was sort of the exposure I needed just to kind of get going.
Yeah, it's interesting because I think there's a lot of talk now about making programming sexy. In a way to try and move it away from the kind of experience that you had, which was very, kind of, I guess, social, like you were by yourself and it was quite clunky or...
Yeah, it was clunky and a little antisocial.
Right, exactly. And also, you weren't programming in assembly, I guess. So it
wasn't quite that low level. BASIC was designed to be easy to learn. It was meant to be sort of an educational programming language. Yeah. So I guess it worked in that sense. Yeah. So yeah.
Interesting. Yeah, I never really had that experience. I feel like that's an experience that's shared by a lot of people, and probably people that you've met in your adult life have also expressed. Yeah. Like a lot of people that go on to build tech companies and things have had this
I think certainly people my age and a little older who were exposed to like the 1980s generation of PCs where like, pre-GUI basically, where it just drops you into a command line. Yeah. Either it was completely uninterpretable or you learn a few commands and start doing stuff there.
Yeah, exactly.
Yeah.
No, I think I first learned about the command line once I finished high school and did an internship as a software engineer. And it was quite interesting because that was my breakthrough moment where I was like, oh, this is actually what a computer is. Yeah. And just this realization that everything that you can do on your computer normally you can do in the command line. And in fact, the GUI is just like built on top of this quite bare bones command line structure.
It's like when you were young, did you ever think that that in your TV there were just like lots of little people running around and like acting things out, and there were like lots of little sets, and like that was how it was working?
I don't think I did, but
I think a lot of people probably had this experience, at least from what I've heard. It's almost like that moment. It's like, oh, there's just like a whole bunch of stuff running around inside the computer, like doing things, except it's actually real.
Yeah, there's a similar idea which I think about a lot, which comes up in physics if you study physics, which is that for any phenomenon that you ever have understood or have like some knowledge of, there's always like a level below that you could go to if you wanted to understand it more deeply. Yeah. And sometimes you have to resist the temptation because it will like distract you from the thing that you're trying to learn now. But it's also like a weird kind of connection where, if a ball falls off a table or something, or if a computer does something, then fundamentally there is some explanation at a lower level for why that thing happened.
Sure. Well, it's the reductionist impulse. It's and some of the, I guess, like intellectual arrogance of physics comes down to this idea that like, well, we're studying the bottom of the stack of reality. Right. Like we're getting as low as you can go, and everything else is just an applied version of our field. But to the point where I think there have even been some sort of overblown publications recently claiming that like, oh wow, you can, how would you put it? basically claiming that they've almost discovered the concept of high-level explanations of phenomena, which did you like Scott Aronson had some I mean he's very good at sort of throwing cold water on sort
Scott
of
Aronson's
anything.
Great, I think,
Anything getting kind of hyped up in sort of popular science. But I'm trying to remember exactly this one. It was claiming to be sort of a mathematical framework explaining the idea of different levels of explanation. And it's sort of like, well, you didn't really need to like invent a whole new framework to make the point that there are different levels of explanation that are useful for different things. It's only if you spend so long at the bottom of the stack that you almost forget that there are other ways of explaining things that are completely accurate, or as accurate as you can get for that level of complexity.
Yeah, and actually it's quite interesting. So I did philosophy of science for my thesis at undergrad, and one of these ideas came up, which was sometimes you can have explanations that are actually more valid at the higher level than they are at the low level.
Sure.
And the classic example in physics is statistical mechanics, where if I tell you the temperature of a system, that's actually much more useful than telling you the individual movement of all the particles at the low level.
Sure.
Just because there are so many different combinations of movements of particles at the low level which correspond to the same temperature. And actually knowing the temperature of the thing is a much more predictive quantity. And in theory, you could derive the temperature from the low level piece, but it almost seems like you're missing something that's quite fundamental if you just focus on the low level trajectories of atoms rather than being like, oh, this object is at this temperature.
Yeah, well, of course. It's I majored in physics in university, and after getting sort of deep enough into the subject, I guess at a certain point it just kind of dawns on you that it's just an elaborate bookkeeping system. It's like you have a certain system of interest, and there's certain quantities that you want to keep track of, like, where it is, where is it going, how's it jiggling, things like that. And at the bottom, physics is like a very, very formal set of rules for, doing the right kind of bookkeeping. And having, at least that's how I came to see it at a certain point.
Okay, can we unpack that a little bit more? Like, there's never an idea that struck me when I was studying physics, or I never heard of anyone talk about it in that way.
Well, think of like what so much of physics comes down to conservation laws, conservation of energy, conservation of momentum, conservation of angular momentum, and each of these has very powerful consequences, because it means that by sort of calculating this quantity that has to be invariant, you can put very, very strong constraints on how a system has to change with time. And this is it's a powerful calculation tool, but the actual calculations you're trying to do essentially come down to, where is this system going to be at some point in the future? If this system is here now, where will it be in the future? Or what will come out of this measurement if we run this experiment? If we put a sensor on the other side of these two slits, what are we going to measure? And by having these rules that constrain the way things can move, you can keep track of all the different forces acting on the system, keep track of all the potential energies, keep track of all the different particles, and if it's a fermionic system, then the number of particles is conserved and things like that. By keeping track of all these different variables that describe the state of the system, you can, with whatever degree of accuracy you want, depending on how much you're willing to turn the crank and calculate, figure out what will come out of that measurement. And that's that at the bottom is physics A to Z, is the rules for doing this bookkeeping, for figuring out what you're gonna measure at the end.
Okay, that's interesting. Because I think some language that I definitely encountered was this whole idea of like dynamic equations and boundary conditions. So that's really what you're trying to find is you have your equations for how things change, and then really you have your boundary conditions which almost define the problem space. And then once you've got that, it's basically just like number crunching. But the challenge becomes that when you're bookkeeping, you often have lots and lots of different things to keep track of, and they each like matter to different degrees. And some things that don't seem particularly relevant might show up later on, or some things that seem very relevant would just like cancel out and disappear towards the end.
Sure. And I think like a lot of the game of at least theoretical physics is coming up with elegant ways of sort of juggling that bookkeeping so that, you know, you reduce it to the minimum number of things that you have to keep track of.
Right.
And as you said, cancel out the terms that you don't need.
Right.
And, you know, do some very, very sort of complicated, like algebraic jujitsu to get out sort of things that you can do in whenever possible in closed form on, you know, with pencil and paper. Because it is a field that has such deep roots. I mean, going back to, you know, Newton and Kepler and guys like this, when it was all, you know, chalkboards and quills on parchment and stuff like this.
Yeah, it's so interesting that Newton, like a lot of his proofs were just geometric proofs where he was just drawing diagrams. That I was quite blown away when I saw some of that stuff. Like he was proving the laws of gravity, but just doing it using diagrams and drawings.
Yeah, and that he just like kept it locked away in like a drawer until he was like 40 or something like this.
Really?
And, so I think the derivation of elliptical orbits as being a consequence of the square root law of the force of gravity. I think that was, you know, Robert Hooke, or whatever his name was, Hooke, came up to Newton at some point and was having this debate with, you know, some other astronomer that, you know, I think like this is a consequence of that. And Newton's like, oh yeah, back in university, I just like proved that and stashed it away in my papers. And Hooke's like, are you kidding me? Like, this is revolutionary. Like, how do you possibly do that?
Yeah, because he was super young as well, like 1666.
Yeah, it was something like that.
His kind of annus mirabilis, whatever his equivalent was. I think he was only like 23 or something. 24.
Yeah, well, I think it was that he was actually on break from university because of plague. Yeah, like they had just shut down. I don't know if it was Cambridge or Oxford, but
I think he was. I think
so. He was a
maybe
professor at Cambridge, but or was it?
Oh, was it? It's true. I thought he was at university because he was like hiding from the plague and he didn't want to get the plague, so he was kind of like holed up in his room and had plenty of time to work on stuff that he cared about.
Or in any case, he was avoiding the plague, which was, you know, what I called it whenever I skipped classes. But interesting. And just thought like, oh, this is neat. Like my classes are kind of boring. I guess I'll just like invent calculus while I'm hanging out. Yeah. So
Okay. So one question that Anna said that I should definitely ask you is this question of physicists, and have you noticed that lots of physicists seem to get, you know, to a certain point in their career and then shift off in different directions?
Well, yeah, there just aren't that many jobs.
Is that something that is, I don't know, do you like take any insight from that, or do you think it's important in some way?
Do I take any insight from physics or from the fact that so many physicists leave the field?
The second bit.
The second one. A lot of it's just like, I think there's a certain type of young nerdy guy, again, usually a guy, but you know, I think there should be more women in the field. But a certain type of young nerdy person who says, you know, all right, I want to study the most fundamental thing. Yeah. And there is this real sort of physics chauvinism that, you know, as I said, we're the best field because we're at the bottom of the stack of explaining reality in physical terms. It's right in the name of physics. And then in the course of studying it, you know, you make it to university and you say, okay, well, I probably need to get a job at some point. Or you sort of look at what the current state of research is and you say, okay, we've got 400 years of accumulated knowledge in this field. It's pretty well worked out. The interesting open problems, either they're more applied or they require, you know, collaborating on some giant multi-billion-dollar project like CERN or something like this, and they look at the actual job prospects. Like, for instance, I think the number of PhDs in physics in the United States today, I don't know the exact numbers, but it's something like a factor of 10 larger than it was, you know, before World War II, when, you know, guys like Feynman and that whole generation of American physicists were being trained. And of course, back then, all the best minds were being trained in Europe. But the field today is just so much bigger than it was than in the kind of the legendary period of sort of early 20th century. And things like the standard model of particle physics were kind of worked out in the 60s. And once you kind of get up to the current state of the field, you get this feeling of, okay, well, maybe the exciting intellectual frontier today isn't in this field, or you just say like, this was fun to study, but I need a job.
Yeah, no, it's interesting. Yeah, I always thought it was interesting that we spent, in my senior year, we spent a while studying superfluid helium, and a lot of that stuff
which is cool.
Yeah, it's like super cool.
Yeah.
Well,
I think it's cool. Yeah.
It is, yeah, very cool.
Yeah.
But yeah, a lot of it was figured out like 100 years ago, and we're still kind of repeating experiments that have been done from like a while ago.
Well, physics has a very high moat to climb over. It's high moat. That's mixing metaphors. High wall to climb over, or a wide moat to cross.
Right. Yeah. It does feel like you can spend. It takes many years to get to like the 1920s and the 1930s, and
sure.
All, like the Maxwell stuff. And
sure.
Before you can really approach. Yeah.
And in every class, often you're just studying the same thing, but in a sort of more stripped down, elegant way.
Yeah.
Where it starts out as like, here's what a force is. Like everybody when you rub amber with a cloth, like it attracts things to it, and stuff like that. And by like an advanced degree, it's like, all right, now we're framing it, and in a fully relativistic framework where it's everything's in 4 vectors, and it all just becomes sort of abstract math. But you can write like all the laws of the universe in 3 lines or something like that.
Yeah, that's really interesting. There was a common joke that was just like at the beginning of every year, your physics professor would just say, okay, everything I taught you in the last year, just forget about it, because it's like, it's all wrong. And we're going to tell you the truth this year. And then it would inevitably be superseded the next year when you like went into more detail.
Sure. But you come out of it really, really smug.
Okay, interesting. Do you feel like it was helpful? So I always thought the people that I was most impressed by in physics were people that could just like look at an equation and like visualize the physical quantity or the physical thing being described. I mean, I think I developed this intuition a little bit with like e to the I theta, and you could be like, oh, that's a wave. Like, we're describing circular things, or we're describing, and there are professors who could do this with linear algebra, especially, who could just look at matrices and be like, oh, that's an upper triangular matrix with this thing there, so it must be this kind of system, and it must behave in this way.
Yeah, I think that's a critical and really underappreciated part of mathematical reasoning, is that the people who are the best at it are able to combine the algebraic and geometric views of any problem. They're able to both see the symbols and use that, again, basically as a bookkeeping method to be like, here are all these different things that you have to keep track of. I'm just going to write down terms for all of them and then have rules for how I can manipulate them. But also to have the sort of intuition for what to do with those symbols. It really does take some kind of geometric reasoning ability, by which I mean an ability to sort of visualize what the different parts do. For instance, I don't know if you've read Surely You're Joking, Mr. Feynman.
Yeah.
But he writes a little bit in that at one point about how he would go talk to mathematicians, and they'd throw problems at him, and he'd say, whenever they'd start describing something to him, he'd sort of say like, okay, well, I'll imagine this is like a fuzzy tennis ball. And then like this particular thing is like the color of the tennis ball. So I'll visualize a blue tennis ball. And then this particular, operation is like rotating that tennis ball in a certain way. And then I'll just know, because like a blue tennis ball doesn't have like orange stitching on it or something like this, that that this particular theorem can't be true.
Interesting. Yeah, I guess the challenge becomes,
and I think he was just sort of like wildly synesthetic in that way, in that he was able to so freely mix his like his visual geometric intuition with the actual symbolic rules. And some people approach math just as a set of symbols, and I think actually if we teach that geometric thinking more, I think that maybe actually could sort of help with sort of math phobia that often people get, because they'll just kind of look at this and they'll be like, I don't know what to do with this. It's like I'm often literally just like looking at Greek.
Yeah. No,
so,
yeah, exactly.
Yeah.
No, there's a really good YouTube video series by Three Blue, One Brown. Have you seen these?
No, I haven't. No.
They're kind of like geometric interpretation of linear algebra concepts. And so he'll talk about like, what does the determinant mean? And if I do a change of basis on a determinant, then why doesn't it change or whatever? And how is it affected and all this kind of stuff. So it's really good. I guess tying a few things together. I think one of the reasons people potentially leave physics is because they realize that they're not Richard Feynman after a few years of study. And,
apparently, even a lot of people in physics left physics because they realized they weren't Richard Feynman. Apparently, a lot of people who crossed paths with the guy were like, wow, there's just no way I'm good at as good as this guy. I'm just going to quit the field.
But yeah, I mean, because when you grow up, you read about people like this and Einstein, like, oh, wow, that'd be so incredible. And then, you meet people that are super brilliant, and it's often quite just like...
Yeah, but I think also this kind of hero worship, and I think physics is especially a field that is rife with this sort of great man hero worship, actually can be really damaging for exactly that reason. Yeah. Like people think that there's just this sort of like innate genius that you have to have. And, the people who do have that innate genius become legendary, but 9 out of 10 people who can make, really important contributions to the field are just, they just get up every day and they just work hard and they just, they struggle with it just as much as everybody else. They're just stubborn and determined. Yeah. So, I think if more people had that kind of grit, and even for me in my research career, hearing stories about how Oppenheimer in the middle of grad school was like on the verge of like dropping out and stuff like that, hearing things like that really can help, realizing that everybody struggles and everybody kind of has imposter syndrome, that sort of thing can, I think, help people just starting out in research, like push through some of the really difficult parts. Yeah. And I think there does need to be more of an acknowledgement of that in academia, because it's not just physics. It's any sort of branch of science will have this hero worship. I mean, I heard that they had some straw poll at Harvard asking people if they could get a Nobel Prize but would die in the next 5 years, something like that. Okay. Would they take that bargain? And I think more than half of the people polled said they would. Granted, maybe a lot of these people were pretty late in their careers, so maybe some of these might have been emeritus professors who were like, well, I've probably only got 5 years anyway. Yeah. But that kind of attitude, I think, is kind of insane.
Yeah, no, especially like in the world that we're living in now, where you're getting more and more co-authors on any given paper, and
sure, there are just more people in science today than there were, and science is becoming more and more collaborative. Though, in my own work, I maybe push against that a little bit. I think for sort of large experimental projects and things like that, like collaboration is definitely necessary. There's just too much technical complexity for one person to do it. Yeah. But I think it's tough to do anything really conceptual in a large group.
It's interesting. Yeah. Let's discuss that a bit more. Yeah, the joke that I heard about Feynman was that the way that Feynman solved problems was like the Feynman method. Have you heard this? Which is...
What is it? Just like write it down, think very hard, and then write down the solution?
Basically, yeah, exactly. And most people are like, well, I probably can't do that.
Right. Well, there was only one Feynman, but there's still thousands of successful, hardworking theoretical physicists who do very good work and make contributions to the field. Yeah,
it's also interesting that a lot of these big breakthroughs kind of come on the cusp of a lot of work that has been done. So like, I think when you learn about Einstein and you realize that it was only because of this, like, like if it wasn't Einstein, it would have been someone else, just because the moment was so ripe for...
Yeah, well, in special relativity, there's a reason it's called, Minkowski space and the Lorentz transform and all stuff like this. These were the guys who were also, on the verge of coming up with special relativity. Exactly. I mean, Minkowski taught Einstein differential geometry. He just had some sort of vague intuition and sat down with a mathematician who just like very carefully tutored him for a long time. So also, like, even Einstein wasn't afraid to ask for help. Yeah. Like even Einstein knew when he didn't have all the tools, and found good mentors and found people he could talk to.
Yeah, it's interesting. I was at a talk this week about the origins of the internet. I think Tim Berners-Lee has been to a lot of events this week, and one of the things they were talking about was when the internet was created, it was kind of this idea that, okay, if we're ever going to build another atomic bomb or work on a project of this size, we're going to need some way of organizing information and being able to like index things and build associations between different pieces of information.
And share cat videos.
I mean, share cat videos. But I mean, this kind of complexity that grows as the size of the problem that you're trying to work on grows.
Sure.
You do need kind of better tools to be able to deal with that.
Well, I mean, I think the Manhattan Project is an excellent example of that, which is still mind-boggling to me that people were able to do that, with 1940s technology, or sort of inventing the technology for the second half of the 20th century. But if you have like 10, 15 spare minutes and want to read something really interesting, the conversations between captured German nuclear scientists when they found out about the existence of the atom bomb was actually recorded. This was, after Germany surrendered, but before Japan did, and these German scientists were being kept under observation by the Allies, and the transcripts are just amazing. But what you get from that is not any surprise at the technical feat, but surprise at the organizational feat. They all knew that it was possible, but they thought that the sheer organizational effort required to produce that much fissile material would have taken 15, 20 years. Oh, wow. And that the Americans were able to do it basically in 3 years was just completely flabbergasting to them.
Purely from an organizational perspective. That's so
pretty much purely from an organizational perspective.
Super interesting.
Yeah.
It's interesting because when you read about the history of the British Empire and things like this, you kind of get this sense that, the British rule the world basically based on bureaucracy, and they were just much better at, but you can't do this because you don't have the correct paperwork for it, and just managed to
right, the importance of having a system.
Exactly. And it was just very well
that and Gatling
system.
Guns.
I mean, yeah, exactly.
Doesn't hurt. Well, it hurts some people, but doesn't hurt when you're building an empire. But that, I guess, that's good for conquering the natives, but you're not going to maintain control unless you have a strict system of rules and things like that.
Yeah. Have you noticed living in England the difference in
the weirdest thing to me has been how polite the police officers are.
Oh yeah, it's great.
It's ridiculous. Like, they're so nice.
I think like a year and a half ago or 2 years ago there was a push because they didn't want to be seen to have like a bad reputation. And I definitely noticed this, that police officers would be like, "Hi, how are you? How's your day?" And would sometimes like leave the interaction by saying like, we're public servants and we're here to help, and we're, you can always come to us if you need anything. And it was very.
I mean, mostly it's just amazing to me that most of them don't even have guns, like, to start. Like, that's great coming from America. But they're. I got pulled over for biking through a construction site and was like ready for them to, got super defensive because I lived in New York before this, and the police in New York City are almost like a paramilitary outfit. And put on my best like aggressive dealing with the NYPD face, and they were just like, "All right, don't do it again, like, carry on." I was like, "Oh wow, okay."
It's like a comedy sketch.
And then I'm like, "Sorry," and, this is suddenly found myself apologizing for doing things, becoming more British by the day.
It's like the Tai Chi effect or whatever, where it's like if you just if you're less aggressive, then somehow if neither person has guns, then it's like much easier.
It's actually de-escalating. Yeah, it's amazing.
Okay, I'm just gonna do a quick sanity check.
Sure thing.
To make sure everything's working. Be back. Let's just make sure. Okay, that's good.
All good. Still on.
And that's still on. Yeah, there was one where I just like stuff went off and I didn't notice. But okay, so the next question I have is, you mentioned a little bit about this conceptual, I don't know the exact phrasing that you used, but this idea that working alone is sometimes more helpful to get to the conceptual foundations of whatever you're working on.
Yeah.
Which then touches on like collaborative, like open office spaces, and a lot of discussion that happens in the tech world about what is the best way to get things done. And we've talked about Claude Shannon, who also seemed to be this kind of quite closed, like thought things through himself a lot. And I'm curious, like, what your experience has been of working with others versus just like sitting in a quiet room by yourself sometimes and figuring things out.
I think I'm lucky that I have the space to work on things in seclusion when I need to. I feel like the whole move in the tech industry towards open offices was probably kind of a reaction against the whole 90s dullness of the gray office cubicle sort of environment. Like, so many of these tech companies, maybe like Microsoft or IBM, already existed for a long time before that, and the new generation, the Google and Facebook and Amazon, all of this came out, around the same time of like when Dilbert was really popular, and when Office Space came out, and this sort of age of cubicle ennui.
Right.
and they wanted to be, you know, the young hip company.
Yeah.
And so they said, all right, you know, we'll just banish the cubicle, no cubicles, because nobody wants to be in a gray little box. It's sad and depressing. And while I'm certainly happy not to work in a cubicle, I feel like the thing that often ends up actually happening in open offices is, at least for me, is I spend most of my day just putting on my headphones and trying to focus on things. And you know, when a conversation does strike up, I either feel like sort of sorry for not joining in, or just like annoyed that people are interrupting my flow. So I don't think that they're a great solution. They certainly create like very dynamic looking offices where everybody sort of, you can just sort of survey the whole floor and see everybody working away very industriously in sort of a kind of panopticon like way. But yeah, I don't know what a better solution would be. It would be, you know, in my ideal world, maybe just everybody would get their own corner office. You just have an office that's some kind of fractal office building that's just all corners. So everybody can have a corner office looking out onto the other corner offices.
It's just like all corners and
all corners,
David's
totally flat,
world.
no hierarchy. Like, yeah, that's the dream. Every mannequin.
Oh yeah, well I think like Joel Spolsky has a lot of talk about this. Where he's like everyone should have their own office, and but it's interesting to me, not necessarily from like how do we design offices type perspective, but more how do we learn on an individual level, because I do think that I experience this, and a lot of people experience this, which is that it's easier than ever to offload memories and things on just you know, if I need to know something,
I barely remember what I did last week. It's all like it's on my calendar and stuff.
Do you think that has affected the way that you think about problems or can think about problems? And this comes back to physics actually, because I know a lot of professors when I was younger would carry little calculators around with them, and you know, would absolutely know Planck's constant, would absolutely know the speed of light in multiple different units of measurement, and would know all of this stuff like really quickly.
Maybe when I was like in the middle of my PhD, or not even in my PhD, I was in a completely different field. But even in the middle of my physics degree, I was possibly could cite like, you know, the permittivity and permissivity and all that sort of E&M stuff. Could just sort of crunch that by hand, but it's like I definitely forgot that as soon as I stopped taking undergraduate physics classes. As soon as you have to stop sort of cranking through stuff with pencil and paper. Yeah, I think there's still some sort of cognitive load to that, just because it makes it harder to just kind of do the sort of thing where you're just sitting on the subway and just thinking like, oh, well, about what order of magnitude is this? About how big is this? Because just thinking about the right magnitudes and scales becomes more difficult when you forget this stuff. I find myself doing derivations a lot less than I used to, and not even necessarily remembering like exactly the papers that things appeared in. But I also think, I mean, working in machine learning and artificial intelligence today, so many of the papers that I see are just kind of different combinations of the same ideas over again.
Right.
It's like people know maybe 5 different tricks, and they just figure out every single possible combination of those tricks. And it's less about really like thinking through a very clear set, like I feel like people don't maybe have the variety of cognitive tools that they used to, except the really good people in the field who you know, have really studied the stuff not just deeply but also broadly, and have a real facility for bringing in ideas from many places. But yeah, that takes commitment, not just to like working on coding up things really hard, but a commitment to sort of going back and revisiting your old study material over and over again. One of my currently living intellectual heroes is Chuck Stevens at the Salk Institute, who was a physicist by training, but now is a neurobiologist, and is one of the few guys who both takes really good like physics thinking, like thinking about scaling laws and deep physical principles, but also just knows the actual biology like extremely well and does very technically sophisticated experiments, and just like is not sort of like flaky when it comes to that sort of
Yeah.
thing. And apparently he'll do a sort of summer school every year where he just goes back basically to sort of, you know, maybe not the Feynman lectures exactly, but sort of things at that level, like the physics fundamentals, and just refreshes his memory on that. Just sort of like an athlete, like a basketball player just practicing their free throws or something like that. It's just about, no matter how good you are, no matter where you are in your career, just going back and practicing the fundamentals.
Yeah, that's a really interesting idea, actually, because I think there is definitely a level of respect that I feel like I have for people that are able to explain concepts very lucidly and are just able to,
definitely.
like not be hand wavy and not be flaky and just say specifically like this is what it is, and you can tell immediately that they understand it very well. And then there is a contrast, I think, with, so I'm working as a software engineer now, and it's actually like often not super helpful to keep a lot of things in your head. Like what's actually more useful is if you're able to trace through pathways in the code, and if you're able to kind of the skill set of being able to like navigate a computer really quickly is often like the thing that makes or breaks whether or not you can understand a complex system.
Are you the kind of guy who just sort of hacks things until you figure out how to make it work, or do you actually try to like, do you read all the docs? You like go through a tutorial on any new framework that you're trying to learn, or what's your approach there?
Probably a mix of what you just said. I think it's like I think I usually go through tutorials on things. I don't usually read the docs until I need to like find something. So I think you usually have a sense of like what's in a particular package, on whether it will be there or not, and then you can look at the docs when you're actually trying to implement something. I think I've learned a lot more about software design, I think. Coming from a physics background, I didn't really appreciate properly the benefits of modularity and like how to structure your code and how to work on large code bases, and like why it's a bad idea to mutate variables and things. Like things that seem quite superfluous if you're just hacking together like a script for physics or whatever, just some kind of experimental thing.
For sure.
But then when you work on a large code base, you notice that, you know, if you have a mutating variable somewhere, then 3 months down the line, it's definitely going to cause a bug and someone's going to have to fix it. And it gets very annoying. So you focus a lot more on trying to design systems well. And I noticed that one thing that was actually quite important is you have to design software which maps to your conceptual models really well. And if you have a conceptual model of an object or whatever it is, and it can't do the same thing in code, then you end up having to hack around it and be like, oh, we can make the code do this weird thing, which then makes it look like the thing in real life. And then you just start running into lots of trouble because...
It is, in some sense, another kind of mental bookkeeping. It's having an idea, again, not just symbolically, like what are the different variables, but, you know, in memory, what are the different things that exist? How can they be manipulated? How persistent are they? It's just very, very large scale algebra in a sense.
And it can be done well and it can be done badly, I think. The strange thing about software engineering is that you don't get told if you're writing bad programs, I think, immediately, like in the sense of there's not that much feedback and it only comes later on. And so you see the benefits like
and so much of the challenge of large scale software engineering is about sort of, well, honestly, it's like running the British Empire. It's just bureaucracy. It's having a good system for code reviews and you know, having taking the time to, you know, write good design docs and actually think things through carefully, which is not a skill that I have.
Which is why the label of like architect seems to make more sense, I think. I think it was Microsoft that originally started like software architect. And I think when you take it seriously, you do see the importance of like good architecture, because making a bad decision early on can just really screw you over later on in terms of your data structures and things
but it's architecture that you can't visualize in the same way.
Yes, exactly.
It's architecture in symbols instead of in building material.
You can draw lots of flowcharts and things. There's actually, so another question I have is, so when I was young, like 15, 16, and was reading about the scientific revolution and this kind of the Enlightenment and rationality coming up as a way of thinking. One idea that I had quite a lot, which is, okay, so in the 1800s now we know all of these things using the scientific method, and Galileo has taught us all these things. And we're as confident in our beliefs as people in the 12th century were about their religious beliefs. And so they believe that true knowledge comes from scripture and from religion and things like this. And we believe that it comes from science and thinking things through. then just kind of by inference, this is a terrible argument, very hand wavy,
Mm-hmm.
but surely there must be some other thing that comes next, which is, oh, all those weird mathematical calculations that we were doing, they were fine for where we were in our evolution of science.
Yeah.
But there will be something new. And I guess Stephen Wolfram has this argument about a new kind of science, which is a little bit overblown, but it's kind of this
some
idea,
of that self-promotion.
Yeah, but it's essentially this idea that like the mathematical tools that we have for physics in the like 18th, 19th, 20th centuries were great, but really it's going to be supplanted by computation, and computation is the kind of new mathematics of problem solving.
Yeah, well, I mean, I don't agree with him that cellular automata will be the new foundation of all science,
Yes,
but
exactly.
but the idea that computational science is kind of a third way of doing science that's neither really experimental science nor theoretical science, in the sense of like coming up with theories and like scribbling equations on again with quill and parchment, that I do agree with, and that actually was a big revelation to me, and part of what led me on my current path, where I really do think of myself neither as an experimental nor a theoretical scientist, but as a computational scientist, essentially writing simulations of model systems, and sort of picking the right model data and running sort of experiments with code, rather than either strictly calculating things or testing physical things.
That's interesting. It's interesting that you choose simulation and this idea of running experiments, because one other way to view computation is, just a really great calculator, where now if I can't find algebraic solutions to my complex integrals, then I have a numerical solution available. And I think some people do think of it that way, the way computers are mostly useful in the sense that they give us access. Like the fundamental problems are the same and the fundamental techniques are the same, but now we just, it's almost like having more time to sit and solve your integrals.
Well, for a lot of, well, certainly for computational physics, for a lot of that's the case. It's like you still know what Newton's laws are, you still know what Schrodinger's equation is, just come up with better ways of turning the crank, or scale up the crank turning to levels that are not possible with pencil and paper, which is why I found when I finally came across machine learning, and honestly a lot of statistics, which seemed like a very dry and boring subject when it was first taught to me, but thinking more deeply about it became kind of more interesting the more I learned. Physicists usually start from the idea that they know the rules of the system, and they do simulations to derive the consequences. And statistics and machine learning goes in exactly the opposite direction. It's that you have observations of a system, you have data, and you try to work backwards to figure out what the underlying laws of that system are.
That's interesting.
Yeah, at least
okay.
At its best, that is what it can be. Now, this is what people in physics would usually call phenomenology, because it's not actually about deriving things from first principles, but, just fitting data, which is seen as, I think justifiably is seen as a somewhat less elegant level of explanation.
Right, because that would be my next question, is that, okay, I have some phenomenon, I have some set of phenomena, and I create a neural network which is able to predict the n plus one like element. But the neural network itself is not particularly explanatory, and it doesn't tell me that much. It's just a set of numbers, basically.
I've also had this debate both with myself and with other people many times, and kind of the conclusion I've come to is that neural networks can be very, very good engineering, but in that sense, they're also very, very bad science.
Okay.
They can be very useful for, detecting certain events. People have done great work on using neural networks to detect certain types of particle events in particle accelerators, things like that. Pierre Baldi's group has done very interesting work there, and there it's essentially scaled up statistics. But actually, that particular use case, they're saying, all right, the theorists come up with a new proposed particle, then you run tons of simulations, and then you train a neural network to detect what those events would look like. So there you already have a potential explanatory theory, and the neural network is used as a kind of sophisticated sensor for telling you whether that theory is right or not.
Okay.
And when you're trying to learn a neural network just to do prediction, that is, I think, a lower level of explanation.
Right.
And I think for industrial applications like speech recognition, image recognition, where you're not trying to come at an explanatory theory, you're just trying to build a product that works, that's fine. That's great. If that's what's the most efficient, use it. Go for it. Cool. Yeah. If you're trying to come up with a theory of how intelligence works, I don't think training a deep neural network is the end of the story. It can be a step on the path. And one interesting trend in neuroscience and psychology today is training these deep neural networks to do cognitive tasks or to do neural tasks like object recognition, and then going in and using this as, again, a computational model to experiment on in a way that you can't experiment on in a physical system. Go in and probe it and sort of tweak parameters and do sensitivity analyses and things like this to try to figure out what features this thing is responding to,
right.
As a way of possibly motivating more simple, elegant theories later on.
Okay, yeah, this is.
But I don't see it as the end of the story. Some people might be happy just with, okay, if we have a neural network that can do everything that this particular animal's brain can, this, the nematode worm is solved if we just have a dynamical system that does everything that it does. And I don't think that's there's more than just data fitting. There are deeper levels of explanation.
Right. Which then gets into the super philosophical stuff of what is an adequate explanation.
What is an explanation? And that sort of thing, exactly.
But I have seen things that are quite similar. When you learn about neural networks and handwriting recognition and things like this, you always see, these, like when you have your convolutional layers or whatever, and then you have these set of neurons are looking for these kinds of edges or looking for flat lines or looking for this kind of curved shape. So there is that kind of thing, I guess.
Yeah.
And you said that people study... Is that what they're studying, or are they studying something different about neural networks? Are they trying to piece together like which parts of the neural network are looking for which types of things in the images or in the data set?
All of the above.
Okay.
It's a fertile field. There are a few people in particular, Dan Yammans and Jim DiCarlo and a handful of others, who in some pretty groundbreaking work showed that the features of deep neural networks trained for object recognition, the intermediate layers. So you're only optimizing this network to put out good predictions at the final layer. Yep. You're not really imposing any constraints except through the architecture on what goes on in the middle layer. Deep neural networks trained so that the output reproduces what the deeper layers of the primate brain do. The features in the intermediate layer better predict the responses of neurons in intermediate parts of the brain than any of the best theories that 4 decades of vision neuroscientists have been able to come up with by going in, designing different sets of stimuli, showing them to monkeys, and going in with probes and recording directly.
That's super. So if I read that,
really interesting.
If I read that in like the news media, I would be like, okay, this is clearly overblown and people are just sensationalizing a news story.
Well,
like to what extent are neural networks very similar to human brains? Because I was always told that they not.
Well, it's the sort of thing where the correlation goes from like 20% to 30% or something like that, or maybe 40% if you're lucky. So I'd say, until you can exactly predict what the response will be, it's not solved. So there's still lots of room. And I should say this is only predicting the first like 1/10 of a second of what happens when you look at an object, because there are massive amounts of feedback in the actual brain. And, the first glimpse we have of something is often wrong. And our brain is kind of constantly we are constantly updating our beliefs about what it is that we see based on new evidence, or just spending longer staring at whatever it is we see. I mean, the process of seeing something is itself dynamic. You don't just look and then have a fixed representation. You're constantly interpreting and reevaluating what you're looking at.
Yeah.
I mean, you talk to any artist, and they can tell you that the more they work, when they work in different ways, it trains them to see the world in very different ways. So perception is an ongoing dynamic process, which mostly for practical reasons is something that isn't really addressed so much in these deep neural networks, just because it takes a huge amount of computational power to run these things.
Yeah.
So just for efficiency, you kind of put everything through in one pass, and you can maybe do a few iterations on top of that where you use more sort of top-down information to update what you see. But for most tasks, just having a really big deep network, is the sort of thing that will get your score higher. So in that sense, there is still a very big gap between biological vision and computer vision, but it was very surprising to me and very surprising to a lot of people in the field that even these models were still better than, even though we don't really know what they're optimizing for, they still discover these representations that are better than anything, the most clever and hardworking neuroscientist has been able to cook up in 40 years. So that was quite startling.
That's pretty interesting. Yeah, and we talked a little bit earlier about Demis Hassabis and this idea that study of the human brain can be actually quite informative when you're designing neural networks. And I think you disagreed a little bit, and you mentioned that your work had been the other way around somewhat. The more, so I should say, so my PhD was in computational neuroscience, kind of the same degree that, or not the same center, but in the same field as some of the DeepMind founders. And the deeper I got into studying neuroscience, and especially sort of trying to figure out the origin of some of these ideas, the more you kind of see how there isn't really a sort of one-way road that these ideas go. Often they're these sort of ideas that have been bouncing around from field to field for decades. And often what the neuroscientists are doing is really taking ideas that the psychologists had, or people in other fields had decades ago, and trying to search for the neural substrate of a particular behavior or a particular hypothesized cognition. So when people talk about neuroscience-inspired AI, often the ideas in the neuroscience itself are ideas that people have sort of said, well, this should exist in the brain somewhere. Right.
They're very rarely, there might be a few exceptions, but they're very rarely driven by the sort of detailed experimental results. It's not that common that something sort of pops out of a neuroscience experiment, and then the computational people look at that and say, wow, that's a computation we didn't even know the brain could do. Because in some sense, to interpret the results of an experiment, you have to have a framework for thinking about what kind of computations the brain might be doing already. Right. Okay. So okay. Often, or maybe I should unpack that a little bit.
It's interesting. From what I got from it is that the human brain is so complex that you have to kind of approach it with this very structured hypothesis already. Yeah. And so when people end up finding things that they were kind of looking for, we shouldn't take that, as seriously as if they had just been studying it kind of objectively.
Well, you can't. I don't think you really can study this stuff objectively. I mean, there are some people who take, again, a sort of super data-driven approach where they say, let's focus on the technology and try to record as many neurons as we can. Let's just try to record everything that the brain is doing, and sometimes shrink down to very simple model animals, like the nematode worm that has only 302 neurons, or
I've heard about this stuff, like the C. elegans.
C. elegans, exactly. Whoops.
Was that you? Yeah,
that was me. Sorry.
So I've seen things like that, or connectomics, I think they call it, where you can actually map out every single individual neuron, and you can watch the kind of firings.
Where they say, let's forget even having a frame at all for thinking about what the brain might be doing. Let's not have these sort of hypothesis-driven experiments. Let's just get as much data as we can. And they've made a lot of progress with this. But often there, you just end up drowning in data. Yeah. And so then they sort of say, all right, we'll put the responsibility for interpreting this on, the next generation of scientists. We'll get the data, then we'll have other people figure out what to do with it. And yeah, so some of it is, I think that some of the best work I've seen in this area probably comes from Mitya Chklovsky's group. Though Sebastian Sung has also done really fantastic work here. But for instance, there are hypotheses on the way, for instance, the flies perceive motion.
Okay.
Different possible simple circuits for how the fly's eye can figure out, am I flying to the left or to the right, or is this object looming at me? When you go to swat a fly and it just flies away really quickly, how can it do that motion computation? The theories themselves were proposed about 60 years ago. They were some of the first neural computation models put out there.
Were these based on observations, or were they based on just kind of
These were just based on sitting down and thinking like, all right, if I were going to design a circuit out of neurons to detect motion, what would be the different ways that I could do it? And one of the earliest ideas was what's called the Reichert detector, which is basically a very simple circuit where you have sort of two input neurons, and then you have two processing neurons, and there's a time delay going from one to the other. So that if you have some object moving from left to right, then first the neuron on the left will detect it, then the neuron on the right will detect it. And if you have a time delay going from the neuron on the left, then the signals will be coincident, and you have a coincidence detector, and the moving from left to right neuron will go off if it's activated in that order, and then you have a similar time delay going in the opposite direction. And if you spend 10 minutes thinking about this, you could probably come up with something similar. If I guess I've spoiled it for you, but if I were to put you in a room with this problem and not tell you what the solution was, it's probably what you would come up with also. So it takes about 10 minutes to come up with a theory. It's taken about 60 years to validate it as true or false.
Oh, wow. Have they done that now? Is that
so
pretty accurate?
I'm not completely up on the state of the field, but a few years ago at least saw a very good talk from Mitya where they went in and did very detailed connectomics of the circuitry of the fly retina and were able to find a certain set of neurons that seemed to have a structure suggestive of Reichert detectors. So it looked at the anatomical level like it did exist. So this is a good case of hypothesis-driven neuroscience combining with the data-driven neuroscience. I think that's a really excellent example of it.
Yeah, it's funny. As soon as you mention it in that way, it seems so obvious. Where it's like, oh, of course, of course, that's what you would do if you were trying to detect the movement of something left to right.
Like I said, it's you spend 10 minutes thinking about it, and you could come up with this.
And so simple as well. You only have two pieces basically. It's
but like biology is hard. So when people talk about neuroscience-inspired AI, I'm like, well, it's easy to generate hypotheses. So it's easy to come up with theories of neural computation. And oftentimes neuroscience-inspired AI is building on these theories of how the brain might work as much as it's building on actual hard evidence of how the brain does work. It's much, much rarer to have really good experimentally supported proof of certain neural computations.
Right.
I think it will become more common as time goes on. I mean, it's a huge field, tons of efforts being poured into it. So hopefully we'll see more success stories like this. This maybe has inspired me to go read up and see if the functional people have gone in and actually measured whether these are Reichert detectors or not. Or maybe one of our listeners can.
We don't have any listeners yet, so it's
but
maybe one day.
Once this is posted, somebody can tell me if this is right or not.
Wow, that's pretty cool. Yeah, it's kind of interesting to see. I wonder if we'll get lots of papers that come out with these conclusions that there's actually this part of the brain which is quite simple to understand and does this function. It's just this.
I think in certainly in like invertebrates and things like this. Well, in mammals also, but in a much more diffuse way. There's clearly a ton of specialized circuitry. And teasing apart that circuitry, we'll get better and better at it. Interpreting that data is still a huge challenge. as I said, because of all these sort of assumptions and frames that people bring with them when they go in to actually to interpret the data itself.
Oh, that's cool.
But yeah, it's certainly, I think one of the surprising discoveries in the last few decades in invertebrate neuroscience is just how much learning does happen in these systems. For instance, you look at mushroom bodies and the flies, and that seems to play a huge role in olfactory learning. So like learning to pair a certain smell with a certain behavior. So that actually does seem to be quite dynamic. So you have a mix of extremely stereotyped circuitry and extremely flexible circuitry.
It's interesting. Yeah, I read a bunch about Mitchell Resnick and the stuff that he did with social animals. And so this idea that if you have a single ant, then it's not particularly useful.
Yeah.
You can't do very much. But then as soon as you have 10,000 ants, then suddenly they all work together. And the example that he gave was if I'm trying to push a boulder from this location to that location, and every ant has like a rough idea of where that location is, then if they're all pushing on it together, then you'll kind of cancel out the bits that are wrong and they will get pretty close to the final location.
Yeah, it was like ant colony optimization, like a popular idea back in the 90s. And I think bringing it back to Douglas Hofstadter, I mean, he writes quite eloquently about a lot of these ideas of distributed cognition or very simple units that aren't very powerful, combining together to produce more, emergent, more intelligent seeming behavior.
Yeah. I haven't read too much of Hofstadter stuff, but the Mitchell Resnick stuff I read was super interesting. And he has all these he does simulations of ants and he gives them very simple rules. Yeah.
Well, I think the Hofstadter stuff is more sort of at the pop science level of like, here's a thing that could exist, or here's a way that it could work.
Yeah, I think now they've gotten onto like robotic bees and things like this, and nanorobots. And
cool and terrifying.
Yeah, exactly. Have you seen the Black Mirror episode of?
Oh yeah.
It's quite scary.
Was it didn't expect to be living in the future, but well, here the fuck I am, or something like this.
Possibly.
Am I allowed to swear on this?
Sure. Yeah.
Okay. Cool.
We have no rules. It's
fantastic.
It's not the BBC.
Yeah. Exactly.
But yeah, no, all of that stuff seems really cool, and they have. I've definitely seen coordinated quadcopters and things like this where you have some very heavy object and one quadcopter wouldn't be able to lift it alone, but you can get 3 or 4 of them working together, and then you can
that's fantastic work. That's very cool.
Assistance or things like this. Yeah, I think that talking to you, I've just become suddenly a lot more excited about technology, which is interesting because I think
funny because I was mostly talking about neuroscience, but
but just this potential of like we are. You've mentioned a lot of moments where we have understood things that potentially seem quite difficult, and I think that's almost like coming back all the way back to the beginning, which is the physicist's kind of tick that gets you going in the beginning, which is, oh wow, I never knew that this weird complicated thing that seemed like it was completely impenetrable is actually understandable, maybe with a bit more than 10 minutes of thinking.
Or just like studying algebra, just keep working at it until you have that aha moment.
Yeah, exactly. That's really cool. Okay. Do you want to talk more about AI and neural networks? Are you interested in GANs and things like this, or do you feel like
we can get onto the generative stuff. Well, I feel like if I talk about generative adversarial networks, I'm just going to probably end up on some drunken rant about why I hate them.
Okay.
No, they're
maybe we can talk about AlphaGo.
They're an interesting idea, but no, let's talk about unsupervised learning some.
AlphaGo 0 is the.
No, let's talk about unsupervised learning.
Okay. Sounds good.
Because I feel like the field has not necessarily suffered, but it's set expectations in a weird way by calling a lot of these models generative models, as opposed to unsupervised learning, because I think it places too much emphasis on the generation.
So when generative models, is that like WaveNet stuff, or is WaveNet
that includes WaveNet, that includes generative adversarial networks, that includes variational autoencoders, that includes good old-fashioned graphical models. For anybody who was doing machine learning before 2012, that I think of generative models as anything where you have a sort of causal model where you go from some kind of latent parameter or representation to generating samples from generating samples that are meant to reproduce the training set. And I realize even in defining what a generative model is, I'm sort of reproducing some of these issues that I have with calling it generative models. Whereas unsupervised learning, I think, is more a broader idea of taking any sort of unstructured data set where you don't have labels, and sort of as I was saying about doing like reverse physics, it's figuring out the laws of the observations or the laws of the data strictly from the observations themselves.
Yeah.
And you can see those. You can see those. Some people might see those as the same thing. Some people might not. And sometimes it's not necessarily about finding the underlying laws governing the data, but about finding some representation, some kind of code, or some kind of simpler representation. So in the same sense that, like deriving physical laws is about finding a progressively simpler and simpler explanation for physical phenomena, unsupervised learning is sort of finding simpler and simpler representations for some very, very complex observations. When you frame it that way, I think it's much more broader than just generating data that looks like the training data, which is particularly, at least for people who work on generative adversarial networks, is kind of the beginning and the end of what they mean by generative models.
It's interesting. And when you phrase it in that language, it kind of makes you think about dimensionality reduction and PCA.
Yeah, dimensionality reduction and PCA are special cases of this also. They're kind of in any sort of machine learning class, this would be like the sort of introductory version, PCA being kind of the linear dimensionality reduction. Or you can, if you are a probabilistic machine learning person, you could think of it as estimating a certain probabilistic model of the data by maximum likelihood, where it's a certain linear generative model with uniform noise. And so all these different, then there's sort of maximum entropy interpretations of, or I guess maximum mutual information interpretations of PCA. It's just having all these different conceptual tools for what it is gives you kind of different ideas for how you might generalize it or how you might build new models based on it. So again, sometimes just going back to the fundamentals and revisiting it and just thinking about it in a different way can inspire different ways of viewing the same thing.
Yeah, that's cool. But what have GANs being used for so far?
Making pretty pictures mostly.
Okay. Is it?
So the funny thing about generative adversarial networks, the thing that I think distinguishes them from what a lot of other people try to do with other unsupervised learning, is that generative adversarial networks are a case of what you would call implicit inference, where you have a model of how to generate data, but you don't have a way of evaluating the probability of that data. So it's like you can roll dice,
right?
To sample, but you can't actually say how likely that particular roll of the dice that comes up is.
Wait, say that again. So
it's like imagine you had a pair of dice. You could roll them. You can roll them as many times as you want. It's really easy to roll them.
Yeah.
But if you say, okay, it came up with 6, that's very likely. Or it came up with snake eyes. That's really unlikely. You can't actually quantify how likely it's. With a GAN, it's like you have dice that you can roll, but you can't say how likely that particular roll is. And what that means is it's very easy to except instead of generating, it's more like if you rolled dice, took the particular numbers on those dice and set those as like the color of a particular pixel in an image, because usually people use generative adversarial networks for computer vision applications.
Yeah.
And people have tried lots of things with sequence generation and text applications, but I'd say it's less mature than the computer vision applications and the computer graphics applications. So people have done lots of interesting stuff with creative applications with GANs because they produce these really sort of interesting visual effects.
Is this the same as the image style transfer?
You can use it for image style transfer. Okay. The original paper on artistic style transfer, the one on make your selfies look like Picasso, was not specifically using generative adversarial networks, but you can do that with generative adversarial networks also.
Okay.
The issue I have with them, and so they're great for creative applications. They have a really interesting sort of texture to them that I know a lot of artists doing really interesting work with that. As machine learning, I think they fall short of what you can do with a lot of other models, because you can't actually, it's very, very difficult, not impossible, but it's difficult to evaluate new data with these models. So as I said, it's like you can roll the dice, but you can't say how likely that roll of the dice is. You can generate data, but you can't say how typical new data is. And what this means is that you can't really say whether or not your models are overfitting, or it's not easy to say whether or not your models are overfitting, which is kind of a very basic thing that you want to be able to say in machine learning.
Right.
Almost all of machine learning is concerned with like proving that you're not overfitting. And yet GANs, because they're so hard to evaluate, you can get away with doing all sorts of stuff that just wouldn't really be kosher in the rest of machine learning.
Okay.
Now, again, sometimes, you know, there are interesting applications where maybe you don't worry too much if you're overfitting a little bit. Maybe you care more about generating very convincing images, but you only need to generate one. So for instance, super resolution, like if you want to sort of zoom in on an image and say like enhance, there you only need to really generate one convincing way of filling it in. You don't need the full distribution over possible images. But then if you want to do any sort of analysis on that upsampled image to say like, okay, if you wanted to, you know, use it what they use it for in all these sort of crime dramas where it's like, oh, you have this blurry photo of like the prime suspect's like car and you can't read the license plate and you want to zoom in. If you did that with a GAN, you might generate something that looks a lot like a license plate, but you would have no reason to believe that that's actually the true license plate. It would be very good at making something convincing, but you wouldn't really be able to... I would not be convinced that it had actually sort of good, sort of proper bounds on how likely different actual license plates would be in that case. I wouldn't trust the results for anything that actually depended on getting it right, as opposed to just making it look convincing. Yeah,
that's interesting. That's something I talked to Andreas about quite a bit as well, because it's a big difference between because so WaveNet, there was this paper that came out recently that was you take one person's voice and you get them to say something, and then you can convert it into a different voice. And the question of whether you can convert it into just a different voice generally versus like Barack Obama's voice or Donald Trump's voice or someone specific was quite a big deal, I think. And I don't know if it used GANs, but
there are different technologies out there for doing this. But I mean, it's at the moment, it's just, if you have the data, it's just a matter of trying out as many different architectures as you can. So like fake news is about to get a lot scarier.
No, that's the thing that
it's crazy. It's crazy.
Do you think that we're far away from that? Because some people argue that we're already there. Like we've already lived with Photoshop for 10 years, 20 years, whatever.
Yeah.
And we've already seen a lot of fake news. And, you know, when you see a picture of Kim Kardashian, you don't really believe that it's completely undoctored.
I think for people who are just sort of casually scrolling through Facebook or something like that and seeing all this stuff, you see so much junk already anyway that as we've sort of seen in recent elections, often sort of trust in the media has already, for an unfortunately large number of people, kind of gone out the window. But I think it will become increasingly hard for even experts to be able to distinguish this stuff, and that's what's really scary.
Yeah, you don't think we'll fall into like the uncanny valley where it's like somewhat believable but still not quite there? Or
I think the frontier for what's believable will keep getting pushed further and further out.
Yeah, and I think the interesting thing politically from this kind of stuff is that you don't need to actually produce something that's genuinely fake. You just need to have enough to sow a seed of doubt in whoever is reading this.
That's the thing is even if the truth is out there, like if you kick up enough dust, it can become really hard to separate fact from fiction.
Yeah, so it's like I don't need to believe that this image was doctored or whatever, it's fake. I just need to have a slight suspicion that it might not be 100% true.
Yeah.
And then it's like, okay, well, I just have this huge barrage of information. So
yeah, it just needs to become exhausting enough to sort reality out from just believing what you want to believe.
Yeah.
And that's the sort of thing that keeps me up at night.
Yeah. Well, it's also just having the energy, I think, to
Yeah.
which is something that I think about a lot, in the sense that it feels like we're moving towards a world which is more relative, where it's not completely clear what the absolute truth is. And I think this has been happening for a while, where you're expected to be able to entertain uncertainties and to be able to hold, almost like a probability distribution, and in your mind have like, well, this is 0.76 likely to be true or something, and keep adjusting.
Well, there's an old Jewish saying that the sign of an intelligent person is somebody who can keep two simultaneous contradictory thoughts in their head.
Yeah.
Though that's also the kind of classic definition of neuroticism, is if you believe if you can't make up your mind between two contradictory beliefs.
That's interesting. I've heard the same thing argued for the marshmallow experiment, where the kid gets given a marshmallow, and it's basically can the child entertain the idea that I really want this marshmallow, and also if I don't eat it, I'll get more reward later.
Yeah, I guess I think of that more as like like an immediate versus long-term reward thing, rather than like.
I think that's the traditional way of interpreting it, but I have heard the other one, which is like
that it's also about an ability to entertain two contradictory thoughts.
Yeah, and I don't know whether one of them is more true than the other.
Yeah, I hadn't really thought about it in that framework before.
But I think this idea of fake news spreading more and more is quite scary, and it'll be interesting to see what happens in the future, whether people develop more robust mechanisms for figuring out what's true, or.
Well, this is why I only get my news through a very, very carefully curated Twitter feed.
Oh, really?
No, kidding.
Don't really Donald Trump streets.
Exactly.
Yeah. So I guess so today I was at a talk about AI and the UK, and it was all about AI policy, basically. I think the government just launched this new report called the Industrial Strategy Bill or something. It was like a white paper on and basically just opening up new pots of funding for things like innovation and technological innovation. And one of the ideas was that potentially with a view to Brexit and things happening like that, we want to retain the talent that we have and this expertise that we have. So especially in fields like AI and technology, it seems like the UK is doing reasonably well for its size. Yeah.
Well, it's interesting to me that there has been such an AI community that has sprung up in London, and some of that certainly comes from the strength of the universities in the UK, no doubt, but also the sort of its location as a hub in Europe. And I heard somebody say once that London's basically just one big airport.
In some ways, people stay for a few years and then go off to their next destination.
Yeah. But it's also just a place that sort of people get in and out of so easily that you can have it as this sort of central hub for so much different stuff. But yeah, I don't know how you have an industrial strategy post Brexit. That I hadn't actually read the report. I mean, what was sort of the summary? Yeah,
I haven't read the full report. I just went to this talk, but in general, it was new fund. I think there's like 750 million or something. Okay. In that region available for grants and things for research and technology.
Okay.
And then there's a whole extensive plan. I need to actually read the commentary to see.
Well, what would be interesting to me is how they actually evaluate different proposals for sending out this money. Because I've sort of seen, I mean, I spent 5 years living in the Bay Area, and have friends who work in VC, seeing sort of as more and more money and power goes to Silicon Valley and goes to tech companies, and as they get into research, seeing how they decide on what is worth investing in versus a more sort of traditional government-funded academic research. I'm not really convinced that the private sector is actually doing it well.
Okay.
I think often when it comes to private investment in research or VC investment in sort of deep tech companies, a lot of it feels really trend-driven. Often you don't have technical experts actually evaluating these these proposals, you just have sort of people getting a quick stream of pitches to them, and nobody knows how to sort of sort out the really like technically meaningful things from the crap. Whereas seeing how like in neuroscience, the NIH in the U.S., the National Institute of Health, is this sort of decades old system of study groups and different panels where they get experts together to sort of read and evaluate and basically peer review different grants, and it's all done much more in a sort of senior expert driven way.
Okay,
and there are trade-offs between them. The more VC-like models sort of saying, we don't know what's going to work, but we want really revolutionary ideas, and we might not be the technical experts, but we'll just sort of invest broadly and just see who comes back to us with interesting results. That can work for starting up companies, and it can occasionally lead to more, for instance, in fields like nuclear fusion, you see a lot of ideas that had fallen by the wayside in academic research, getting some lifeblood from some very, very deep-pocketed funds.
Oh, really?
Some very well.
That's interesting, because I always thought with nuclear research it was like the big government-funded projects are the only ones that have any shot.
Most of the money is in the big government projects.
Yeah.
But in certain areas in academic research, either for reasons of, in the fusion field specifically, I think a lot of that comes down to shrinking budgets and sort of people becoming more conservative because they have a much smaller pie to fight over. But often just having these very rigorous sort of senior domain expert-led panels can often lead to the really crazy proposals getting rejected because it's seen as sort of flaky or not serious.
Right.
And so you fund more serious but also more incremental proposals. And this was a lot of my frustration with sort of academic neuroscience work. So I think it's very rare that you can see the combination done well. But I'm don't know too much about their industrial strategy. I guess this was what got us on this topic originally.
Yeah,
but I'm curious, not just what they intend to invest in, but how they intend to decide on the sort of social process of intending of deciding on who's worthy or not. Seems to make such a big difference in what takes off and what doesn't.
Yeah. Okay, cool. Yeah, and I think we both have to spend some time and actually read this, because I think it was just released yesterday. So here's the summary.
Key policies include ideas, raise total research and development, R&D investment to 2.4% of GDP by 2027. Sounds nice. Increase the rate of R&D tax credit to 12%. Like, okay.
Yeah.
Maybe under people. Establish a technical education system that rivals the best in the world. Okay, who can object to that?
Yeah, it all comes down to the details, I think.
Yeah. Invest an additional $406 million in maths, digital and technical. Sure. Create a new national retraining scheme. Yeah, sounds great.
Yeah, I think one of the interesting points that came up in the talk today was this idea of diversity in STEM fields. And so the lady who was giving the talk basically made this argument that if you just have one kind of person designing these algorithms, then you're going to end up building a system that only suits one kind of person. Or do you think that that's a real like, to what extent do you think this is a significant problem that we should all be
God. I don't work on applications too much, but when it does come to applications, like so many people who work in tech, they live in a bubble. The ideas they have are influenced by the problems they see around them, which are very different from the problems most people have. And they build tools to suit those problems. When it comes to sort of big tech companies, I think the wave of interest and investment from tech companies in machine learning mostly comes down to having these very, very large online systems with real time people interacting with them in real time, and you've got these ridiculously enormous streams of data, because every time a user clicks on your website, that's 1 bit, or actually many bits. And just suddenly having this instrumented system for gathering data from billions of people that had never existed in this real-time way, that had never existed in history before.
Yeah.
Like, these are the kinds of problems. But the problems there will be, how do we make the services on our website work better? How do we use this stream of this fire hose of data that we're getting work better? So when people say artificial intelligence, at least in sort of the current wave of excitement, I think the current applications mostly come down to things like this. I think the future applications could be much more, I hate to use this, it's such an incredibly overused word, but I'll say it anyway, disruptive.
Yeah.
The most interesting potential applications to me, and in many ways we're still far away from this, is taking this technology and getting it out of our computers and into the real world.
Yeah.
Because, we sort of started this by talking about, babies staring at screens. I mean, how much time do we spend in the computer's world today?
Yeah.
Getting out of bringing the machines into our world.
Yeah, there was a lot of talk about this a few years ago, I felt, when people were talking about different kinds of user interfaces. And there was a great bit in a Steven Pinker book where he was talking about how incredible the human hand is. And basically it's like, you can, if you're a mechanical engineer, then the human hand is able to do all these different kinds of movements. It can hold a pencil, it can hold a bucket, it can throw a frisbee, it can, there's all of these incredible things. And yet, like, the main mode of interacting with screens is like a touch screen that you have one finger and you just prod a piece of glass. And it seems like such a shame that that's the primary way of interacting with a computer or a keyboard. Or just
Douglas Engelbart, when he was first building the mouse, it wasn't supposed to just be, point and click and maybe right click. Not that anybody points and clicks that much anymore even, but it was supposed to be more like a keyboard where you would play like chords on this device that would have 3 or 4 buttons, or I guess you could do a thumb button also. So it would really be like more like playing a piano one-handed. And so you could have all these sort of rich combinations, but it was just like too much for people to memorize all of these different combinations like that.
It's interesting. I remember out of Y Combinator, there were a few companies that did these things where they built wristbands and things where you could do different gestures, and as you were moving around, you could control.
While we're talking about that, let me use this as an opportunity to talk up my friends at Control Labs, who are, a lot of people have tried that. Not a lot of people have the neuroscience and expertise in EMG recording to actually make that work. These guys were colleagues of mine in neuroscience at Columbia, working in some of the best labs in the world on motor control, and they've been doing really fantastic stuff. Building one of these some of these devices. It's Control Labs, CTRL Labs, like the control button on your laptop. So yeah.
Oh, sweet.
Yeah.
Cool.
Really amazing team. So a lot of rich machine learning problems also, just trying to do gesture recognition for the device itself.
That would be cool. Like if you could find some way to interact with computers that didn't require you to sit in front of a screen all day. Like I think I've noticed that since I started working as well. It's quite jarring in many ways, and you kind of spend many months and then realize that, wow, I've just been sat in front of a computer all day for God knows how long. So
you can interact with computers more fluidly, but if you can even make the computers be able to interact in our world, if you can give them the powers that our hand has to, pick things up and manipulate them and things like that, even just walk upstairs reliably, suddenly you've got a huge revolution there. I guess the original question was about diversity and how that affects applications.
You kind of did answer that to some degree.
Yeah, touched on it a little bit.
I think that's pretty good, and it's I do see that the phrase that the woman used today. I wish I remembered her name, but she said that you end up with technology that just reminds you of a teenage boy's smelly bedroom. If you just let a single kind of person.
If you let overgrown teenage boys in smelly bedrooms design the technology.
Yes, exactly. So because you want technology that works for mothers and works for people in all kinds of society. And she talks a lot about how we have an aging population, and one of the big challenges is going to be how do we take care of people who are at various different stages of their lives. And so she phrased it but she said that we should try and make social care like a valid, kind of have more respect in society. But there are also lots of problems that people who are much older and who don't use technology as much are facing. And those people probably seem quite alien to the typical technology guy.
Sure.
Yeah.